Okay, welcome to the lecture on Chapter 7 on Ito processes. So that's a natural extension of what we just did with the Ito's formula. Okay, so what's an Ito process? Let's look at the definition. So you always have a Brownian motion in the background, and an Ito process is a process of the form xt. The process is an Ito integral plus a Riemann integral, with the starting position being x0. Okay, so this is obviously Ito, and this is obviously a Riemann integral. Very good. Now, when does that make sense? Whenever the strategy I integrate on is some process for which the Ito integral makes sense, and D here is some process as well where the Riemann integral is well defined, and we want this to be adapted to the Brownian filtration. Why V, why D? V stands for volatility and D stands for drift. We'll see that later. Well, actually, we'll see that right away. Now, remember that we can save some time, and instead of writing those integrals, write the differential. So dxt, which is xt minus x0 if you want infinitesimal, is equal to vt dbt plus dt dt. Okay? Again, this makes no sense by itself. It only makes sense written as integrals. However, it gives us some idea of what this process does, at least locally. So there is some drift. Okay? So how does the process vary in time? That's what dxt stands for, right? So how much it vary in a small, how much xt varies in, let's say, small interval t plus dt. Well, this says that you vary by like a function, a usual function, so dt term times the drift. Okay, that's if you want the trend. And there is some fluctuation, which is given by some underlying Brownian motion, so the Brownian increment dbt, and this is multiplied by some amplitude, which we call the volatility Vt. So the volatility might depend on omega, might depend on time. Okay? We'll see examples. Okay. So note that this is an example of Ito processes. It's later in the notes, but let's do it right now. An example, let's put it here. So example of Ito is what we did last lecture. Is if I take xt to be a function of time and Brownian motion. If I apply Ito's formula, this tells me that the volatility is what? It's the derivative with respect to space, evaluated at tbt. Okay, just look at the form of Ito's formula. And the drift, well, it's a bit more complicated. There's a derivative with respect to time, and there's the second derivative with respect to space. All right. So what we're doing here is essentially generalizing to a broader class of process. So we know that function of t and bt I can write as an Ito integral and a Riemann integral. So let's not look at more generally a process which we can write in terms of an Ito integral and the Riemann integral. In the case where you have this form, then the volatility has some very special form. Great. Okay, this is essentially what is explained here. Okay, now there's an important class or subclass, say, of Ito processes is a term you've probably already heard of, is diffusion. And a diffusion is a process where the volatility, it's an Ito process, where the volatility depends on the position only. So the volatility Vt is a function of the position at xt, doesn't depend on the past, and the drift is the same thing, only depends on the position. So this is called a diffusion, and most of the processes we'll see are diffusions. We'll say it's time homogeneous because it only depends on the position, not on the time. If you were time inhomogeneous diffusion, that means that Vt would be a function of time and position. And same thing with mu for the drift. We will see later that most example we saw, Ornstein-Uhlenbeck process, it's not a martingale, but it's a diffusion, time homogeneous diffusion. What else? Geometric Brownian motion, it's a diffusion. Brownian bridge is a diffusion, and not time homogeneous, and also Brownian motion with drift. All right, so there's several examples. Okay. So now diffusions, the differential of the diffusion, sometimes we call them stochastic differential equations, or SDE for short. Okay, so stochastic differential equation, or SDE. Okay, because it's really the generalization of a differential equation. Okay, so let's say my xt, which is a function of time, was only a function of time, and I don't have any Brownian part, so that would be the equation. So I could rewrite it as if I write xt as just a function of time, there's no randomness. So this is the derivative, send the dt on the other side, this is the derivative of the function, and the derivative is given by the drift. So that tells you what's the rate of increase or decrease at any time. Okay, so what we're doing here is actually generalizing differential equations, ordinary differential equations of the first order, saying that the derivative of the process is given by some slope. Okay, that's the drift term, and we add some fluctuation term, which is sigma xt, governs the amplitude, and then some randomness that, if you write it formally, is dbt dt. Now we know that Brownian motion is not differentiable, so that makes no sense. But what makes sense is to actually multiply by dt everywhere, and what we have is really an SDE. Okay, SDE has a meaning if I write it in terms of integral. So this means that xt is equal to the integral Ito integral plus the Riemann integral. All right. So SDEs are really the generalization of ODEs. Okay. So a diffusion satisfying SDE if, when I write the differential form, I have an SDE of this form. Okay. Let's look at examples. Brownian motion with drift. In that case, this is quite simple. Let's use blue. So this is just Brownian motion with some constant. Here sigma is not a function, it's just a constant. And the drift also is just a constant. And Brownian motion with drift is just sigma t plus mu t. Okay? So if I want to write this in terms of integral, so here actually I start at 0. Is just the integral of sigma dbt, which gives me sigma bt, plus mu. This is a constant. Okay? So when I integrate, so this here I should have s. Okay, I have t's everywhere. And this is it. So actually, if I want to write the SDE of Brownian motion with drift, so the process in differential form is just dxt equals sigma dbt plus mu dt, which is not surprising considering it says this form. All right? So that's the SDE of Brownian motion with drift. The volatility is constant in sigma. The drift is constant is mu. All right. Now let's look at examples where the volatility and the drift are no longer constant. Let's look at geometric Brownian motion. So geometric Brownian motion, where I just take the exponential Brownian motion with drift, that's an Ito process. How do I know that? Well, I apply Ito's formula, and we did that example. If you go back to the chapter, and the function of time and space is just exponential of sigma x plus mu t. You apply Ito's formula, and what you get is that in differential form, dxt is equal to sigma xt dbt plus this constant, so sigma and mu are constant, times xt dt, right? Now, what's the volatility? It's this guy. And what's the volatility here is this guy. It's no longer a constant because it depends on xt. Okay? So it's a function of the position. And so what this means is that the greater the position, the greater the fluctuation, right? Because I multiply the Brownian increment. So if this number is large, then the multiplying the variance, if you want, the standard deviation of this whole thing is bigger. Okay? Same thing here. If xt is big, then the trend is bigger. And you can see that from the picture, that's geometric Brownian motion, right? So if I look at the path, which is quite high, so now the fluctuation is how much I go up and down, and you can see the variation are much bigger, right? Look at this big drop, much bigger than if I'm close to the axis, if the position is not so big. Okay, and same thing with the trend. Okay, so if it goes exponentially, so actually if I'm higher, then the trend is actually more pronounced. Okay. So geometric Brownian motion is a diffusion, and that's the SDE with the volatility depends on the position, and the drift also depends on the position. Now, as I said at the beginning, any function of Brownian motion for which you can apply Ito's formula will be diffusion. The volatility is this guy, and drift is slightly more complicated, is this guy. Okay, so there's a lot of processes that are diffusion. And a lot of processes are Ito processes in general. Okay, so that gives you a huge collection of processes to choose from when you want to model some random phenomena, random time series. Okay, now what about Ito's formula? Okay, so let's say I have geometric Brownian motion, call it ST, and I want to look at a function of t and st. Exactly like I do for Brownian motion. When is this a Martingale? Well, if it were Brownian motion, well, what I would do, I would apply Ito's formula and see if my compensator is 0 or not. But now I don't have Brownian motion, I have geometric Brownian motion. So it would be nice to have Ito's formula for geometric Brownian motion. And we do. Okay. And so what's the idea? It's exactly as before, that is, let me add a page here. Okay, so what's the idea? Well, I would take FTST, and I would do Ito's formula, Taylor expansion to second order. So let's do it in differential form. So I would add this, blah, blah. Okay. Now the derivative of, with respect to space, is evaluated at ST and not BT. The ST and not the BT, let's emphasize that. Now the second order in time I don't care about. Then I would have the second derivative with respect to space, the ST square, and then I would have the mixed derivative. Okay, now what do I do? Well, I know that the ST is some volatility times the BT. Oh, here it would be dST times dt. VT dBT plus big DT dt. Okay, so I can replace that here. Okay. Now, okay, so let's do that. So I would have delta TF dST, which is VT dBT plus dt dt. Okay, good. Now, what do I do with this guy? Well, I apply Ito's rules. So rules of stochastic calculus telling me that dST times dt, well, is VT dBT plus dt dt multiplied by dt. But dt dBT is 0 and dt squared is 0, so this is 0. So this whole guy is 0. Okay? So you see how I apply the rules of stochastic calculus? Now, what about dST squared? Put in pink. Well, apply the rules of stochastic calculus. What am I going to have if this is square of that? Well, I'm going to have dBT squared. dt dBT is 0. So the only thing, if you apply the rules of stochastic calculus, the only thing you're going to have is VT squared dBT squared, which is VT squared dt. And that's the other term. Okay? So I'm doing it in general, not necessarily for geometric Brownian motion. Okay? Great. Now if I put all this together, what do I have? I have that dFTST is equal to, I'm going to group all the dt term together. There's more now. I have this VT squared so I have, what do I have? I have this dt from here. I have the VT squared dt from here. It's multiplied by the derivative. Okay? So you have to be careful here because there's a lot of derivatives, so you take your time. Okay, so that I have. And then this dST, I have a term in dt, which is this times that. So I get the dt term is plus delta xf TST dt. And there's a term in dBT. Okay. And the dBT term, let's take our time, is this guy. So I get plus VT delta xf TST dBT. Okay. Let me double check that I didn't make any mistake. The Ito's formula is right here. I think that's correct. Okay. So by applying Ito's rules, so it's nothing is surprising here. I know that a function of t and st can be written as an Riemann integral with this integrand and the Ito integral with this strategy. Okay? Now, I don't want you to know this formula by heart. For a specific example, you work the function, you do your derivative. What you do is you do the differential to second order like I did here, and you apply Ito's formula. It takes some practice, but if you keep your work clean, it's going to work fine. Okay? Now, you learn something doing this, and that's important. Let's put it in a nice color, green. Okay? Observe that FTST is, again, an Ito process. So anytime you take a nice function of an Ito process, so here the only thing I said is that ST is Ito process. Okay? It has some volatility, some drift. You take a function of that, it's still an Ito process because I can write it as a Riemann part with this drift. This is the Riemann part. And an Ito part, which is this guy, with this volatility. So Ito processes have nice properties. If you take functions of them, they remain Ito processes. This is quite nice. And you have Ito's formula for them, and you only have to apply the rules of stochastic calculus. All right? Now, where does that come from? Well, it comes from the rules, so you can prove this rule. It says that, remember, for Brownian motion, we had that this rule, dt equals dbt squared, so this was related to the quadratic variation of bt being t. The same way, this rule that we just derived and using naively the rules of stochastic calculus tells you that the quadratic variation of st is the integral of vt squared dt. So this you have to prove, and this the content of proposition 7.3, that if you have an Ito process of this form with this volatility and this drift, then the quadratic variation is the integral square of the volatility ds. Okay? Again, this is clear by applying, well, you have to prove it, but to remember it, you just apply the Ito's rule. So it's consistent with Ito's rules. All right? Now, how do you actually prove Ito's formula? Now, we just did it using the rules of stochastic calculus, so I can make sure your rules still apply. Same as before, you do Taylor approximation to second order, and then what you would end up using, the second order, would be this result. So I won't do it. Okay, so this is the result that I did. Again, don't learn that by heart. You just have to do Taylor expansion of S to second order, and apply the rules of stochastic calculus. Okay, great. So, all right, so I think I'll stop here. Thank you for listening.